So, family pedigrees, which is just a fancy way of talking about a family tree, really. All right, so family pedigrees are usually used to trace diseases or other sorts of or other mutations, but usually diseases, through a family tree. All right, and so there's two main things you want to be able to think about here. One of them is the disease or mutation, or sorry, the disease, is it caused by a recessive mutation or a dominant mutation? All right. Um, Sometimes they tell you, in which case it's great, but if they don't, you need to be able to figure it out. All right. So I will tell you now that this family tree shows a recessive mutation or recessive disease. Recessive disease caused via recessive mutation. All right. And the way you can tell that, okay, there's one that is the ultimate hallmark, and it's here in the second generation here, 3 and 4. So the idea is that if it's always check your key, there'll always be a key. And so the idea here is that if it's a clear circle, then the person is unaffected. Okay. And if it's colored in, all right, the square in the circle simply means male and female. But if it's colored in, then that means the person has the disease. Right. And so if you look here at individuals 3 and 4 in the second generation, neither of these people are affected, right? So they are healthy, and yet they have children who have the disease. This is the hallmark of a recessive disease, all right? Is that you have healthy people, two healthy people giving birth to a person with the disease. With, stands for with the disease. Now, why? Okay, because think about it this way. All right. So if this is recessive, then you know this genotype. Let's just call it the diseases R and R. Those are the two alleles. All right, can everybody see that? Yeah. So the idea is that if they have the disease, you know that their genotype must be two little r's. All right. Now, if they have two little r's, that means they got one from their mother and one from their father, which means they must each have one little r. But neither of them have the disease. So the other allele that the parents have must be a big R. Okay. And so this is the way you start to fill in. For a lot of these, you can find out their genotypes based on their parents and their offspring. Okay. This is another thing that you can notice from a recessive is that two people with the disease basically cannot give birth to a person without the disease. Okay. Because all they have are recessive alleles. And so all of their children get the recessive alleles. Okay. This is another example here, right? 1 and 2, both of them are healthy, but they have a child with the disease. All right. Now here you have a person who has the disease and somebody who doesn't, and both of their offspring don't. Neither of their offspring have it. So those you can also determine their genotype. You know, so this one again is two little r's. So this one only has one. It must get a little r from its parent, from this parent. Let's say that's the mother. Okay, but it's healthy, so the father must have given it a capital R. A big R. All right. So this is the way that you start to figure this stuff out. Okay. The same thing down here. For example, you know that this one has to have two little r's. Okay, because it has the disease. But then all of their offspring are healthy. But they all must be carriers, right? They all have to have at least one little r because that's the only one that their father could give them. And then they all have to have a capital R. Now, there are some things that we don't know. For example, number 11, we don't know whether this person is heterozygous or homozygous dominant. Having 4 offspring and giving all of them a capital R suggests that it might be homozygous dominant, but maybe they just got real lucky with the odds. Okay. And so there are some genotypes that you won't be able to determine. All right. The same thing up here. We know that each of these numbers 2 and 3 are carriers because their mother had to give them the disease, but we don't know what the genotype of this person is. They could be two big R's, or they could have one big and one little and just happen to give the big R to both of their offspring. We don't know. So there are some things, usually on a family pedigree, you will not be able to determine everybody's genotype 100%. Okay. But you should be able to do it at to the people of interest, or maybe there's two and you have to do 2 Punnett squares to determine their offspring. But the idea is that if it's a recessive disease, this is the hallmark. You have healthy people giving birth to unhealthy offspring. So what does it look like if you have the dominant pedigree is a little bit more difficult. So this is a dominant pedigree here. Again, sometimes they already tell you whether it's dominant or recessive, and you don't have to figure it out, all right? If they ask you about genotypes on these, then the idea is that if this is a dominant disease caused by a dominant allele, all right, then, so here, sorry, let me go back. With the recessive one, you notice I started with the people who had the disease, yes, because I know their genotype must be homozygous recessive. If it's caused by a dominant disease, I start with the people who don't have the disease because I know that they also must be homozygous recessive. I'll do H here, okay? So if the dark ones have the disease, right, and the light ones don't, then I know that anybody who doesn't have the disease doesn't have any copy of the dominant allele, so they must be homozygous recessive, okay? Now, and then you start to play the same game, all right? For example, here, this person has the disease. So we don't know whether they are, we know that they have to have at least one capital H. Same with this person up here. They have to have at least one capital H. Now, how would I determine their actual genotype, right? I know they have to have a capital H, all right? But the idea is that this mother is perfectly healthy. So she gave all of her offspring small h's. So these two must be heterozygous. They still have the disease because it's caused by a dominant allele, but they're heterozygous. All right. The same thing with this one. All right. This one has the disease, but their father, this person's father, must have given them a lowercase h. So they are also going to be heterozygous. Okay. Or you could play the game like this. This person is healthy. They got one lowercase h, one recessive allele from their mother. They had to have gotten the second one from somewhere else, their father. That's the only other person involved in this. Okay. We're assuming that nobody's sleeping around on each other. And so the idea is that that would also tell you that this person must be heterozygous. Okay. Now this person had a healthy offspring, which means they also must be heterozygous. And then this one got the two little h's, and this one had two little h's. There's for the recessive ones, this hallmark of two healthy people giving birth to an unhealthy, or I don't want to call it unhealthy, but a person with the disease, it's not exactly the same thing here. But what you will tend to see with the dominant diseases is that oftentimes once you have healthy people, then it doesn't show back up again, right? If these people were to get married, as long as they didn't marry anybody with the disease, then you would continue to see this branch of the family tree continue to be healthy all the way down. All right. So those are your family pedigrees, and they can ask different things. Sometimes they want to ask you about the chance of two people having an offspring with the disease. Sometimes they want to ask you about the genotypes of people on here. Okay. If they ask you about the chance of an offspring, then you're going to do a Punnett square. If they ask you about the genotypes, then you have to look at, well, what about their parents or siblings or children or things like that. And if they ask you whether it's recessive or dominant, you have to look at the overall trends.